Okay, so maybe this should have been the part of a retro computing track, because it goes as far back as 1968, when Dijkstra sent a memo talking about why GoTo is bad and why we should avoid it. And the memo was then redistributed by Niklas Werf under the name GoTo consider harmful. And that's the original source of the consider harmful phrase. Okay, so what's wrong with the GoTo in the first place, to get some context? You can put it in different ways, but this particular way of putting it is, I shamelessly stole from Nathaniel Smith, who wrote a nice blog post about it. And it goes like this. This is a program in Flowmatic, which is the predecessor of COBOL, and it's an unstructured language. So as you see, there are no loops, nothing. It's not even indented, and you see a lot of jumps there. So you look at a program and you have no idea what's going on, and then you start drawing arrows, how the control flow looks like, and it looks like this. So you look at it and you have no idea what's going on. So what's wrong with that? You have different constructs, if, for, or whatever, and GoTo, and some of them are good, some of them are bad. And how should we know which ones are good and which ones are bad? And one way of thinking about it is, let's say the construct is good if the control flow starts in the top and then it ends up in the bottom. And if you look at all those constructs, all of them have this nice property that it just goes from the top to the bottom. If you do an if block, it can do the if part or the else part, but eventually it will arrive in the bottom. And same for a for or function call or just sequential sequence of commands. But not so for GoTo. For GoTo, it just jumps somewhere and it never returns. It never reaches the bottom of the code block. So we like to believe that the functions are black boxes. We call a function, and the function eventually returns. Nice and then easy to reason about. So we have a main function, it calls function foo, which then calls function bar, but eventually it will return from bar and return to foo. And it's also nice for encapsulation, because main doesn't have to know that foo calls bar. Because you change the implementation, it calls something else, you don't care, it still returns back. But try to use a GoTo somewhere, and suddenly that's no longer a case, right? It just somewhere in the nested function, it jumps somewhere else, never to return. And now here we have developer Bob, who's very cautious. He doesn't use any GoTos, but he happens to use a library written by Alice, who's very cautious as well. She doesn't use any GoTos, but she uses a library written by Colin, who's careless and who uses a GoTo. And suddenly, Bob is hurt by that, because down inside the dependency tree, just control flow, just somewhere else, and Bob's function call foo to foo never returns. All the assumptions he had about his code are broken. So this is it's not only bad design, it's bad design plus because it's transitive. It takes only one dependency in your whole dependency tree and you are screwed. So what I was talking about was the old kind of GoTo that probably not many people here really remember. There were big bad GoTos which could jump around the code base from a function to a different function, and you don't see those anymore, right? But it's actually not that long ago. When I started programming in 1984, I've got Sinclair's Spectrum, and it had built-in BASIC, and it actually looks very much like the Flowmatic code I've shown before. There were GoTos all around the place, and it just jumped around. So you don't see this anymore, but what we have now is this kind of thing. domesticated goto, which can jump only inside a function, right? So that's the goto in C. Like you can jump inside a function, but there's no way to jump out. So it's still bad, but it's at least not transitive, right? So the Colin, the developer of a nested dependency, can really break your workflow. Okay, so now that I've explained the whole like go-to thing like from 50 years ago, what does it have to do with modern programming thing? And I'm coming from the networking background. I'm an author of ZeroMQ, and I've made like several networking libraries. And the problem that occurs all the time is how to handle asynchronous calls, basically. Right? So this is what you have on wire. There's a byte saying that the following field is going to be 13 bytes long, and then you have the actual data. And how are we going to process that? So the old school way of doing that was like classic Unix way, where you launch the process for each connection, and the process was nice and sequential, and it just read this, read that, and that was it. But then people realized that launching a process per connection is probably not a good thing because it's slow and takes a lot of resources. So we have to do better, and so the threads were born. And well, the interesting thing is about threads is you can't really find out like who invented them. But probably the person was too ashamed to actually. Okay. So what we have to deal with nowadays is this kind of thing. We have this async function, which looks like a function, but it's not really a function because you would expect it to do whatever is inside the block and then return as a normal function, but it doesn't. It returns immediately, and then at some later point, the async part is done. So if you just look at this naively as if this was a normal function, you would expect it to print 1, and then to print 3, and then to print 5, and 4, and 2. But actually what you have is 1, 2, and this part is executed 3, 4, and then 5. So it's weird. And yeah, and it gets even worse in JavaScript, where basically those functions are anonymous and nested inside the code. And this looks like a normal structured code, but it executes in very different ways. So the layout of the program has basically nothing to do with the order of execution. Right? So what you see here is 1, 3, 5, 4, 2. What's printed out is 1, 2, 3, 4, 5, I guess. Well, okay. The other option to do it in is classic state machines, where you remember like what state you are in a variable. And well, this is at least explicit about what it's doing. So you are in this state, so you switch to a different state, you will launch a async call, and at some later point the function is called again with the reading done message, and the other part of the state machine is executed. But look at this code, like it's terrible. And this is one slide, but if you look at the real implementation, it's like pages and pages of this kind of stuff. Nobody can really like grasp it at first sight. So then enter Golang. So the nice thing about Golang is that it introduced coroutines as as first-class citizen, and you are back to the old Unix-style programming where you basically launch a process for each connection, and it's nice and sequential. Except it's not a process; it's a coroutine, which means it's cheap. Like the stack is at the beginning like 2 kilobytes, and the context switch is pretty quick, like 20 nanoseconds or something. So, okay, so it seems that we are done. But what's wrong with the goto? With Go construct, launching of coroutine. You see, it kind of looks like the old Go because it's on one way it just continues, but in the background somehow the control flow just jumps away to some different function. It's very similar to Go in a way. So, and you have the same problem as we had before. So once again, Bob launches a coroutine from Alice's library, which launches a call from Colin's library, and Colin does go and launches a coroutine which is running in the background, and the call returns to Bob's code, and Bob thinks, okay, the bar thing is done, but there's actually a coroutine running in the background, and Bob has no idea. So it's transitive again. Like if any of your dependencies launches a coroutine in the background, you have the old problem from 50 years ago with this wild big bad goto. So how easy is it to fix? So one would say, okay, let's make coroutine scoped. Right? So we have a scope, we launch a coroutine, and when we get to the end of the scope, the coroutine will be cancelled, and that's it. Except that doesn't really work because look here, this is the classical code, networking code. So we have a server which accepts connections, and each connection is handled by a handler, which is a separate coroutine. But if it was cancelled at the end of the block, well, it would be actually cancelled immediately, and nothing would happen. So that's not good enough. So what we really need is like two different kind of scopes. One is like the normal scope, and one is like the better scope, which cancels all the coroutines that were launched inside it. Right. So this is in C. This is code using a library that I wrote called libdil. And basically, you see that the two scopes here. There is a thing called like a bundle. It's a bundle of coroutines. You initialize it. There in the while, you launch any number of coroutines inside it. And once you want to shut down your server or something, you jump out of the loop. Here is the break, and you close the bundle, and that cancels all the coroutines. So it's kind of, you see, it's indented, like nicely structured. There are several languages that implemented this. Like this is in Python, a library called Trio, which does the pretty similar thing, except it's nicer. So you open a thing they call nursery, which is the same as bundle in the previous example, and yeah, you basically do the same thing. You launch the coroutines, and once you get out of the block, all the coroutines are cancelled. So, is that it? Is that easy? So there are still some open problems here. We are not yet there. Like for example, there is a difference between how libdil handles the termination and how Trio handles the termination. What Trio does is you start your nursery, you launch 3 coroutines, and when you get to the end of the block, it waits. It waits till all of them are finished, and when they are finished, it just continues. If there's an error in any of them, you just raise an exception, and when the exception reaches this point, it cancels all the other coroutines, and then it continues. Libdil does it differently. So there you open a bundle, you launch some threads, and at some point you say close bundle, and at that point the coroutines are closed. So the difference really is that in this case you have like a kind of like main thread which is in control of all other threads. In the other case, like all of them are created equal, and there's no like the controller and the controlled. So which way is better? It's pretty hard to tell because in the Trio version you have this nice error propagation where you throw an error and the error gets to the caller coroutine and it bubbles up until it reaches main. But the problem there is if that happens, then it kind of looks like that one of the coroutines can cancel its siblings and even its parents, and which is very like unstructured way of doing stuff. So that's not nice about it. So it would be nice to know like whether we can combine the two approaches, that we would have nice error handling and kind of nice encapsulation where a coroutine cannot cancel its parent. Okay, so some other problems that are still unsolved or partially solved. How would we handle timeouts? So one way is to use something like as a Golang context, where you have an object on which you can call like cancel the timeout function, and it will cancel after it, or you can pass it manually to each function. Like who knows what's better. Grace periods, that's a hard problem. So for example, you want to shut down your server and you say, okay, I am giving you like 5 seconds to finish whatever stuff you're doing, to close the connection decently, and then shut down. So we don't have a good story for that.
Okay, I'm sorry to interrupt.
Okay.
We're out of time, unfortunately. The timer started a bit late.
Thanks.
So thank you very much for the talk.